Basically, how did I get all the way to Boston is, I guess, a good question, and getting to IBM. So I basically, also kind of similar, I come from Lebanon, which is also maybe has a bit of a different school system than what is in the US, but usually over there around, I guess, the age of 15 or 16, so like right before high school, you get to choose one of two major tracks, which is something more on the sciencey and math side and something more on the literature side. And again, I was always very interested in math, and physics were kind of my two favorite areas, not so much in chemistry and bio, but still within physics, definitely better than history and geography and all some of these other things, literature, where you need to read books and whatever. So I kind of chose the science path as well, kind of focused on that in high school, and then went into college into an engineering program. Now, how did I choose computer and electrical engineering over the other types of engineering is also a very interesting thing, where I was like, oh, I like computer engineering. I also like civil and structural engineering and buildings and stuff, but I also like cars and mechanical engineering. So let's kind of go with an alphabetical order and apply to them. And it was the way that the programs were called. Computer and electrical came first before the civil engineering, just because it was the acronyms were CCE versus CEE versus ME. And there was I think electrical was in the middle, which was EE. So that's kind of how I got into computer engineering. But it was kind of a funny thing, but it was actually also some of the things that, because I am interested in many different fields, it allowed me, because all of the kind of the trend, right, of everything is starting to become more computer driven and things like that. I was able to explore computers in cars and computers in buildings, and how do you have these models that help you create buildings in a more efficient way and stuff like that. So that was kind of one thing. So my undergrad was computer and communications, computer and electrical engineering. And then my PhD, right after my undergrad, I was like, you know what, I don't feel like I'm strong enough of an engineer to contribute anything in this life. So let's maybe study a bit more. So I went into a PhD. I decided to focus on machine learning, which was kind of the main research area that I worked on. And the reason I chose machine learning was also because it was such a versatile tool that I can study that, and you have to apply it to different domains. And because I can decide what I like, I decided, well, if I study machine learning, I can then study about quantum computers when I need machine learning and quantum computers. I can study about electronics when I need machine learning and electronics. And you kind of start to diverge into all of these different fields, and it's always interesting. So that's how I got into a PhD at the same university where I did my undergrad. And then after I finished, after many, many years, I finally applied for a job, and I came to IBM, to the IBM research lab that is based out of Cambridge, Massachusetts. And since then that was like 2 years ago, not too far in the past. But since then, I've been a researcher in the lab, where I basically apply what I know about machine learning, about AI, about deep learning. We'll get to see that these three terms are actually quite different, on applications that these days relate to business automation and enterprise transformation. So everything related to technology. And that's about it. So yeah, definitely, like in industry and kind of the media, we kind of see them all being used interchangeably. But basically, the way that I like to think about them is AI is this big thing, artificial intelligence, right? So humans, animals, different creatures on this earth have intelligence, and we're trying to kind of infuse it into these machines and these human creations. So AI is basically, what are these tasks that usually humans and animals can do, and we're trying to make machines do? There's a wide range of them. Let's just focus maybe on humans, or just any creature really, where we need to be able to see the environment, right? Perceive the environment that we're in. Maybe we want to act on the environment that we're in. So there's a lot of things that go into being able to move a pen from point A to point B, or to understand that I'm looking at the sun versus I'm looking at the tree, or in the shade versus not in the shade, etc. So all of these different tasks kind of fall under artificial intelligence. So we're trying to infuse these machines with some sort of capabilities that usually creatures of intelligence can perform. But then how will you do that, right? There's some sort of algorithm that we need to write. Machine learning is one family of algorithms that can help us perform some of these tasks, right? So if you wanted to understand language, you can apply machine learning algorithms to try to generate models that understand language. And within machine learning algorithms, there are many different algorithms that we can adopt. There's a subset of that is the deep learning family of them, which have a very specific structure to these algorithms that kind of borrow some things from the human brain, but kind of take it and run with it, basically. We don't really consider them very biologically exact, right? They're more of an approximate model and has a bit more math in it, etc. But basically, deep learning is a subset of machine learning algorithms that attempt to learn these tasks within AI in a way that requires these artificial neural networks and things like that. One thing that we always think about is information is knowledge, right? And now there's so much information in this world that sometimes you can't really process it all, right? So we were able to create all of these electronics that are collecting information 24/7. If you're thinking about the Internet of Things, we're thinking about all of these different things. And the end goal is just like to improve quality of life, to kind of ensure the minimum needs of food and shelter and all of these different things. And we're just trying to do everything better always, right? And keep improving them. So whether that's improving agriculture, like more information, you create more sophisticated ways of harvesting food, less food waste, better for the environment. We're trying to understand, but we're also trying to apply, right? The better we understand things, it touches on many different aspects, right? Health, we become healthier, or we have better medical practices to keep people healthy. Same thing with applying, right? Of whether it's the agriculture or producing or just consuming things in life, more information basically gives us a better way to make decisions. But because we're limited in time, right? All of these natural constraints of physics, of time and space and all of that, maybe we can use computers to help us process more faster, more efficiently, etc. So that's why I think it's important to know about technology and AI and all this stuff. Definitely problem solving is one, learning is another big one. I think this is something where, especially with kind of coming from a very traditional educational system where like you study all the different things, you study things out of a textbook. It's like, oh, I don't know this. I haven't studied this in a book, so I don't know anything about it and I can't solve the problem. The idea here is that you have to kind of continually keep learning new things. Just because something is that you don't know that thing shouldn't block you from solving the problem that you have. I think that's like the biggest thing that we definitely learn when going through a PhD, but I would say we don't need a PhD to learn this, is how do we teach ourselves to learn and continuously learn. I think is the key to, because everything's changing so quickly, right? So like in my undergrad studies, C++ was the programming language. By the time I was about to graduate with my PhD, it was like Python's the best thing to use. So I go and study Python. You can't say, oh, no, I only write C++ code. That wouldn't work. So I would say learning as this next one. I think green computing is something that's like flying under the radar. No one's paying attention to it. But even when like we're at our laptops, we're writing these like deep learning, right? So we know it's one line of code, maybe 5 lines of code maximum. But then it's so much computing power in the back end that a lot of us don't even think about this, training all of these huge models. And it's going to be like a big problem if we're not paying attention to it. And this is actually one of the things where, in my research, I kind of always moved away from big data and deep learning, partly because I'm not very patient in waiting for my results to come back. Like I want them to come back faster, but kind of that impatience sparked some sort of creativity to say, oh, let's start to kind of focus on these shallow models, but then without really knowing it, it's like, oh, but this is a big thing for companies who don't have all of these powerful GPUs, etc. But just because like we're getting to this world of abundance doesn't mean that we should use that abundance, because we're kind of losing something on the other side of it. And just green computing, we hear a lot about pollution, right? Polluting our oceans, polluting land, the air from the cars, etc. But we seem to always forget about the computers and how much harm they're doing, especially these deep learning ones. So I think green computing is a big one.